Dear students, in this module we will learn about the crystal field approach of lability and inertness of the complex. After completion of this module, you should be able to understand about the background of crystal field theory behind lability and inertness of the complexes. You should also get crystal field theory for explanation of inertness and lability of the complexes. And you should also be able to understand about a new term that will be taught in the module called crystal field activation energy and its application for the inertness and lability of the complex. So before proceeding towards crystal field theory for explanation of lability and inertness, let's have background for this module. As we know, under the fixed condition of concentration of substrate, that is 0.1 molar and temperature 25 degrees centigrade, complexes that undergo quick displacement means complexes that displaces their ligand within a half lifetime below 1 minute are called labile complexes, while complexes in which ligand displacement or substitution process is slow is called inert. Explanation provided by valence bond theory was incomplete and had limitations. For example, from valence bond theory, D8 system should be less favorable for associative nucleophilic substitution reaction, but experimentally they were found labile. Also, valence bond theory provides only the qualitative approach for the explanation of lability and inertness of the complex. Because of these limitations, we needed a better explanation that were provided by the crystal field theory. So let's have the explanation by the crystal field theory. So during explanation of crystal field theory, the first important point is geometry of intermediate of nucleophilic substitution reaction are different than that of the reactant or that of the product. Since geometry of both reactants and intermediate are different, therefore crystal field splitting pattern for both of them will be different. As we know, rate depends on the activation energy of the reaction and therefore rate can be correlated with the energy of transition state. Unfortunately, transition state exists for that much small time that structure of reactant or transition state cannot be correlated. One of the factors that includes activation energy of reaction is crystal field activation energy, which is the difference of crystal field stabilization energy of intermediate and reactant. This is because transition state of the complex cannot be trapped, but the pathway can be achieved by the intermediate. So if we have the intermediate, we can find out their crystal field stabilization energy, and by the difference of two we can see whether formation of intermediate is easier or not. So the second point is, in dissociative nucleophilic substitution reaction for octahedral complex, intermediate is of square pyramidal shape. When a ligand is getting displaced from the octahedral system, then in general the structure that left behind is of square pyramidal shape. While in case of associative nucleophilic substitution reaction for octahedral complex, intermediate is of octahedral wedge shape, that you can see in the diagram shown here. So if we find the crystal field activation energy, or if we correlate crystal field stabilization energy of reactant and that of intermediate, then easily we can get whether the reaction can be transformed from reactant to intermediate or not. So crystal field activation energy now can decide whether feasibility of formation of intermediate is possible or not. The difference of crystal field stabilization energy of intermediate and that of reactant is called crystal field activation energy. Crystal field activation energy is one of the important factors among the various that decide activation barrier of the reaction. And if you know about the activation barrier, you can easily say whether the reaction is kinetically possible or not. Since activation barrier is directly related to rate of reaction, crystal field activation energy can be treated as a deciding factor behind lability and inertness of the complexes. For better understanding of theory behind lability and inertness, let's discuss dissociative and associative nucleophilic reaction one by one. In this figure, represent dissociative nucleophilic substitution reaction that involve a square pyramidal complex as an intermediate. Crystal field splitting pattern for octahedral, which is shown in the right side of the diagram, and square pyramidal, which is shown in the left side of the diagram, are given here. For convenience, let's first discuss about a D1 system. In this case, if first electron will enter the least energy orbital, then in case of octahedral geometry, total energy or total crystal field stabilization energy that you can achieve should be 1 into minus 4 dq plus 0 into plus 6.0 dq. Overall, total crystal field stabilization energy would be minus 4 dq. At the same time, if you calculate the crystal field stabilization energy in case of a square pyramidal shape, the crystal field stabilization energy you will find would be 1 into minus 4.5 dq plus 0 into minus 0.9 dq plus 0 into plus 0.9 dq plus 0 into plus 9 dq. Overall, the total crystal field stabilization energy in case of a square pyramidal would be minus 4.5 dq. So, what we get? In case of octahedral system, we had the crystal field stabilization energy equal to minus 4 dq, while in case of a square pyramidal system, crystal field stabilization energy was minus 4.5 dq. Since crystal field activation energy is a difference between the crystal field stabilization energy of intermediate and that of the reactant, therefore, crystal field activation energy in this case would be minus 4.5 dq minus 4 dq. Overall, the value that you will obtain for crystal field activation energy is minus 0.5 dq. It means this complex is labile because overall crystal field stabilization energy of intermediate is lower than that of the crystal field stabilization energy of the reactant, and therefore reaction is feasible to go towards the intermediate. Now, on the basis of different factors that affect crystal field splitting energy, the formed complex may either be high spin or low spin. Crystal field activation energy will decide about lability and inertness of the complexes. Overall, crystal field activation energy for the reaction would be minus 4.5 dq minus 4 dq, means the crystal field activation energy for this reaction is minus 0.5 dq. As you can see here, crystal field activation energy has negative value. By this reaction, intermediate is getting more stability than that of the reactant, and therefore process is feasible. So, this kind of reaction would be feasible for dissociative mechanism. Similarly, if a second electron will enter, then in case of reactant that is in the octahedral structure, the crystal field stabilization energy would be 2 into minus 4 dq plus 0 into plus 6 dq. Overall, crystal field stabilization energy would be minus 8 dq. While in case of a square pyramidal shape, overall crystal field stabilization energy would be 2 into minus 4.5 dq plus 0 into minus 9.9 dq plus 0 into plus 0.9 dq plus 0 into plus 9 dq. The value would become minus 9 dq. So, if you compare the two, crystal field stabilization energy for a D2 system was minus 4 dq, while for D2 system in square pyramidal geometry was minus 9 dq. As a result, if you compare the two, you will find crystal field stabilization energy of square pyramidal geometry was lower than that of the octahedral geometry, and as a result the difference of the two would become minus 1 dq. Since minus 1 dq is a negative term, that is intermediate is more stable than that of reactant, therefore the reaction will be labile, therefore the complex is labile in nature and the product will be easily formed through dissociative mechanism. Third electron enters, crystal field stabilization energy for an octahedral geometry would be minus 12 dq, while in case of square pyramidal the crystal field stabilization energy will become equal to minus 9.9 dq. Since the third electron will enter into a stage of minus 0.9 dq. So, in this case overall crystal field activation energy will have a positive value, that is plus 2.1 dq. So, in this case molecule will not labile for a dissociative mechanism, therefore it would be inert in nature. From D4 to D7 we can have two different type of complexes, that is of high spin and low spin complexes, and in both the cases value of crystal field stabilization energy will differ for octahedral system. So, it is better to calculate them separately. So, in case of D4 high spin complex, you can see the crystal field stabilization energy for octahedral system would be minus 6 dq, while in case of a square pyramidal system it would be minus 9 dq. Overall, if you compare the two in high spin complex, then you will get crystal field activation energy minus 3 dq. Since crystal field activation energy is negative, therefore the molecule will be, or the reaction will be labile. In case of D5 geometry, since it is a half filled case, crystal field stabilization energy for octahedral system and square pyramidal system both are 0 value, and therefore crystal field activation energy will also have 0 value. Since value is not positive, it means the reaction is feasible for dissociative pathway, and therefore we can say this reaction is labile, although will be comparatively slower than that of the other species from the D1 to D4. For your convenience, crystal field stabilization energy for high spin complexes for D1 to D10 system is shown here in the table. Crystal field activation energy will decide about the lability and inertness of the complex. More negative the value of CFAE, more will be the chances of formation of intermediate, and therefore more labile complex will be. Table present crystal field stabilization energy for a low spin complex. So, by the same diagram you can find the crystal field activation energy for the low spin complex. From D1 to D3 the value of crystal field activation energy would be same, that is D1 would be labile, D2 would be labile and D3 would be inert. After D3 system, that is when fourth electron will enter, overall crystal field stabilization energy for D4 octahedral system would be minus 16 dq, while in case of D4 system of intermediate, that is D4 low spin system of a square pyramidal shape, the crystal field stabilization energy would be calculated like this: 2 electron will be filled in the ground state, then single electron, and then fourth electron will be filled in the minus 0.9 dq state. Overall, if you calculate the crystal field stabilization energy for square pyramidal geometry, it would become 3 into minus 4.5 dq plus 1 into minus 0.9 dq plus 0 into plus 0.9 dq plus 0 into plus 9 dq. The value of crystal field stabilization energy for D4 system in square pyramidal geometry would be minus 14.4 dq. That results crystal field activation energy equal to plus 1.6 dq. Since value of crystal field activation energy is positive, therefore this complex would be inert. Similarly, you can find D5 and D6 geometry in low spin case would frame an inert complex for dissociative mechanism. In case of D7, the value will again become negative and the reaction or the molecule will be labile for the dissociative substitution reaction. In D8 case, for both high spin and low spin cases, you can find the value of crystal field activation energy is equal to plus 2.1 dq, means it would be inert for a dissociative mechanism. So overall, the crystal field activation energy and conclusion framed by this value is represented in table. You can get the lability and inertness of the complex from this table. It is clear that complexes containing metal ion with D3 and D8 arrangement are inert, while D4, D5 and D6 arrangements are inert in low spin state only. Now let's move for the associative nucleophilic substitution reaction. Associative nucleophilic substitution reaction involves octahedral wedge intermediate that you can see, and table shows crystal field activation energy for SN2 reaction for complexes containing metal ions in their high spin and predict about the lability and inertness of the complex. Here we are showing only the table for the associative nucleophilic substitution reaction. The splitting pattern for octahedral wedge and crystal field activation energy of complexes undergoing SN2 reaction in their low spin state is intentionally left as a task for the student, and you need to find out the same. Now let's summarize this module. Crystal field theory explains concept of lability and inertness on the basis of crystal field activation energy, which is a difference of crystal field stabilization energy of intermediate and reactant. For SN1 reaction, complexes containing metal ion with D3 and D8 arrangement are inert in both their low and high spin state, while D4, D5 and D6 arrangements are inert in low spin state only. For associative nucleophilic substitution reaction, complexes containing metal ion with D3, D4, D8 and D9 arrangement are inert, while D3 and D9 configuration are inert for low spin complexes only.